Hello everyone. Today I'm going to start on chapter 10, the compression steel members. This is one of the very important topics that we need to understand. So before solving any problems, I would like to go over some criteria and requirements that you may need to know in order to understand the topic and dive into more problems. So PU um, is the factor axial load, which should be less or equal than the phi times the nominal compressive strength. The phi here is always 0.9, the resistance factor. It's always 0.9, and this is our general check. So there is two types of failure modes that we have to be familiar with. First is the local instability, and second is the overall instability. For the local instability, typically our column would be relatively thin, and the buckle it's local. It's at one part of the column, not for the entire column from its title. And for the overall instability, the entire column will buckle. The thing is with the local instability, it'll show you sign of failure in a small local point at any section in the element, point of failure before the entire column is fails or buckles, while the overall instability is the entire column will buckle. So for the overall instability, we have three types of failure modes. First is the flexural buckling, and this is the shape of the flexural buckling. And basically, it will buckle from the weak side. If you wonder what is the weak, what is the strong side, if this is our beam column here, right? This is our I-beam column. So this is the weak side. This is the strong side. So the column typically not easily to buckle this way, but it's easier to buckle this way because here the web is weak as opposed to the flange. So this is what represents you here. So the second failure mode is the torsional buckling. And for the torsional buckling is this scenario when we have load applied this side and we have resistance going in the other direction, then your failure will be in this way. And for the third one, it's a combination, the flexural, torsional, and buckling, which is a combination between this one and this one here. So it'll buckle in this mode. As far as the local buckling criteria, we have two modes or two criteria that we have to look for: unstiffened element and stiffened element. So the unstiffened element, if we look at this angle here, it's an unsupported angle that is parallel to the load. So if we to the loading. So if we apply a load here this way or apply load this way, then the edge of this angle or the edge of this angle will buckle, will bend because it's unsupported. That's why we call it unstiffened. The same case here, like if this load applied in this direction, then this one, this side, and this edge all unstiffened. The same goes here and here, but then we look at this web here, it's stiffened. Why? Because see the two edges on the or the flanges on the two sides. So this element here is stiffened, so as this one here. but this edge and this edge is unstiffened. For a pipe or tube, it's always stiffened, and for HSS shape or rectangular or squared, it's always stiffened. This is the thickness of the shape, and we'll need it to identify the inner shape versus the outer shape. The same for this one here. So this is the unstiffened. From table 10.1, which we'll see in the next slide, if the width over the thickness is larger than the lambda r, this symbol called lambda over r, then it will identify the slenderness shape. So from this relationship here, we'll be able to identify the slenderness. Why do we need the slenderness? We'll talk about it. This is table 10.1, and it's broken down by column. So the first column is the type of shape. So we have W shape, S shape, M shape, H shape, C, T shape, and so on and so forth. The second column is the width to the thickness ratio. So for a W shape, for instance, we have two criteria that we have to check against. One is the flange, the effective width of the flange over two times thickness of the flange, and this is its equation here is 0.56 under the radical modulus of elasticity over Fy. And the second one is the H, which is the web over the thickness of the web, and the lambda value is found from this equation, which is 1.49 under the radical modulus of elasticity over Fy. The magnitude for 36 KSI is this. The magnitude for 50 KSI is what you see here. And the same applies for the rest of the shapes. Now, as far as the flexural buckling criteria, this is what we so-called the slenderness ratio. We need to be familiar with the slenderness ratio, because through this slenderness ratio, we'll be able to identify if our column is elastic or inelastic. So the K stands for the effective length factor. L is the length of the column. R is the radius of gyration. And R is found through the radical moment of inertia over the gross area, all under the radical. That's how you find the radius of gyration. So why do you need to find the slenderness ratio? Because if the slenderness ratio, which is the value from here, if it's above or greater than 4.71 under the radical modulus of elasticity over Fy, then your column is elastic. If the value of the slenderness ratio is less than this value, then your column is inelastic. This is very important to remember. Also, I want to point out the Euler equation is this. The KL over R, everything squared. This is the Euler equation. Why do we need Euler equation? We'll talk about it more, but Euler equation, it's more for buckling and the mode failures and so forth. Now, to conclude this lecture, the code here, the AISC recommends that the slenderness ratios always should be taking less than 200. Always should be taking less than 200.